Hi. In this lecture, we're going to talk about a model that produces a tipping point. It's a very simple model, and it comes from physics, and it's known as the percolation model. Now, the idea is this. You've got ground up here, and you've got water that comes down as rain, and you want to ask, does it percolate through the soil or not? Right? Very simple question. So how do you model something like that? And again, the essence of modeling is to simplify things, right? So what you're going to do is construct the following sort of model, just a checkerboard, sort of like the game of life or cellular automata models. But the idea here is this, is that you've got a bunch of squares, and they can either be sort of filled in like this, or they can be left open. Now the idea is this: you can only jump from a filled-in square to a filled-in square. So think of a frog trying to cross a river. So it can jump along here, along here, along here, but it gets stuck, doesn't make it. And it can go here, and it gets stuck. So this is a case where it wouldn't percolate, because you can't get from here all the way down to the bottom. So here's the model, really simple model. He asks the following question. Let P equal the probability that I fill in a square. So for each square I flip a coin, and if P's a half, then half the time I fill in a square, half the time I don't. If it's a third of the time I fill in a square, and 2/3 of the time I don't. And then we ask, does it percolate? It's a really simple question. Well, here's what the graph looks like. As long as P is less than 59.2%, it doesn't percolate. This is for a big graph, right? But once you get above that, the system tips, right? Right here there's a tip, and then it becomes likely that it does percolate. So you get this really abrupt change. Now notice this is a nonlinear function, right? A linear function looks sort of like this, and this thing goes sort of flat and then makes this tip right at that point. So what's causing the tip? Well, what's causing the tip is that if we look back at the picture, right, for P less than 59%, there just aren't enough things filled in. So if you were at 30%, went to 31%, like if I filled in like one more square, it's still not likely that I'd percolate. But once I get to about 59%, then so many squares are filled in that it becomes suddenly really likely that I'm going to be able to make it to the bottom. So it should be pretty clear that going from 20 to 21% isn't going to have much of an effect. And going from 21 to 22% isn't going to have much of an effect. But going from 58 to 59 to 60 suddenly has a huge effect. Now, what's great about this model is that it can be applied to all sorts of stuff. So we're going to first apply it to forest fires, and then we're going to apply it to banks. So we're going to use a net logo model here to try and make sense of this. And what we have is a model here, a simple model of forest fires. And what we have is you have one button that shows the density. And that's right up here. And then we just set this thing up, and that's going to fill in trees with this density. So currently it's at 57%. And then I'm going to, across this left edge, you'll see, if you look really closely, you can see red. I'm going to start fire along that edge, and we're just going to see what happens if I let it go. So if I let that go, what you see is that, oh, it comes close and it almost makes it. Let's try it again. Let's set it up again. Oh, it comes close and almost makes it. Doesn't quite do it. One more time. Just about, pretty good. But let's move this thing up to then 61%, which is above that 59% threshold. And look what happens here. At 61%, it makes it. And let's do it again. 61% again, look what happens. It makes it, right? 61% again, it makes it. So what we see in this very simple model is that if we go to 57%, right, and set it up, we're not likely to make it. But if we just increase it a little bit, let's just make it even 60%, right, which is barely above the threshold, then what happens is the fire spreads throughout the whole space. So we see this phase transition, right at 59%, from the fire not spreading to there not being a fire over the whole space to there being a fire over the whole space. Okay, so we can think about that forest fire model in the following way. We think of the yield. So suppose we had a forest and we wanted to get as much wood as we could from the forest, but we knew there was a chance of fires. What would our yield curve look like? Well, there's that critical value, right, at 59%, right? And what would happen is, as we planted more and more trees, we'd get sort of a nice linear yield. We'd get more and more wood. But then once we got above the critical threshold, suddenly our yield would fall off really fast, and there'd also be a tip in terms of the yield. So not only is there a tip in terms of the likelihood of a fire, there's also a tip in terms of the yield. So what's nice is, here we've seen again, remember we talked about fertility of models. So we have a model that was used to explain percolation, like why does there seem to be, soil either percolates or doesn't percolate. And we can use that for forest fires. And what we see is that, again, ignoring things like wind speed and terrain and things like that, that there seems to be some density at which a fire is really likely to spread, and a density of trees at which it's not likely to spread. But let's push it even further. Let's imagine we have a model of percolating banks, What would that look like? What do I mean? Well, let's again have this checkerboard thing. And let's suppose that, here's a bank, here's bank 1, and here's bank 2, here's bank 3, here's bank 4, and here's bank 5. Now what we can imagine is suppose this bank fails. It makes a bunch of bad loans. Well, suppose that this bank then has borrowed money from these banks, right? So these banks all have given money, right, to bank 1. But when bank 1 fails, it then can't pay the money back to these other banks. And if it's loaned enough money, right, then these banks may fail. If they've loaned enough money to bank 1, they may fail because they don't get their money back. And so the failure can spread. So remember we talked about that before, about how the IMF has constructed these models of banks where you have, here's a bank failing, and it spreads to other banks failing, and that leads to other failings and so on, right? Now these models are more sophisticated than just bank fails and moves to the next bank. What you do is you write down, sophisticated accounting equations where banks have assets, capital, and liabilities, and they've got loans of different durations, and those loans fail, and you can sort of ask, if we put stress on the system of having a bank fail, how fast does that spread? So the basic premise is the same, this notion of percolation, but what you do is you add more detail, rich, accurate detail about exactly what those loans look like. And then you could ask the question, is there a tipping point in the case of these banks? So is there sort of a state at which the entire system is poised to suddenly have all sorts of bank failures, right? And again, that's a question you can ask in the context of that richer model. So maybe the insight from the simple percolation model will hold in the bank case, and maybe it won't. That's something we're only going to understand by writing down that richer model. Now you can do the same thing in the context of country failures, right? So I put this graph up, I think, in one of the first lectures for this course. So this is a case where we have England fail first, right? And then what happens is, I think, that spreads to Ireland and a couple other countries, and then here it spreads to France or to Germany, and then it spreads down to France. So what happens is you can ask, if one country fails, will that percolate through all the other countries or not? And you can get a sense of, is this whole system sort of poised for some giant failure? In other words, you can ask, is there a tipping point in the system of sort of country level financial systems? All right. Let's go even one further. We can also take the same model and think about information percolating. What do I mean by that? Well, imagine there's some network of people, right? So here's a network of people, and you could ask, okay, if there's some probability that if I hear some rumor or get some piece of information or know something, that I'm going to tell it to my friends. Right? So now instead of there's just probability that things are going to move across links, I can ask, as a function of that probability, what's the likelihood that the information percolates, that everybody hears about it, right? And I can use the same model. And so what would the model tell me? The model would say, well, if a rumor is juicy enough, or if a piece of information is important enough, then it's really likely to spread. Nobody's likely to hear it. If it's not important enough, then it may not spread. So here's what's really interesting. Let's go back and think about information percolation. You might think, here's the value of a piece of information, or here's how juicy, right, a piece of gossip is. And here's sort of how many people hear. So here's the number of people here. Now you might think, well, that should be linear. The more valuable the information, the more juicy the gossip, the more people should hear. But if you actually construct a network model, right, that looks something like this, and assume that there's some probability of people telling people across links, what you're likely to get is something that maybe has a bit of a tip, right? That nothing happens if it's not very juicy or the value of the information is pretty low. It doesn't spread. But then once it gets above some critical threshold, like right here, it takes off, and almost everybody's likely to hear. And so this says that we should expect the distribution of information, the distribution of rumors, not to be sort of very in a linear way with how interesting the information is or how valuable it is, but instead to possibly have this kink, to possibly have this tipping point. And the reason why is because information spreads through networks, right? And because it spreads through networks, you get this same sort of percolation phenomena. Okay, so interesting, right? We took this percolation model from physics. We saw how it gives us insight into forest fires, and even gives us insights into possibly how information, spreads through a system, spreads through a graph. Okay, let's have just a little bit of fun here. Let's, sort of really take the shackles off. We've got this model, and we've got this model about sort of percolation, moving from one thing to another. Well, we can apply this